Hi, we at the Yeh Labs at the California Institute of Technology would like to describe to you our recent work on magnetism-induced massive Dirac spectra and topological defects in chromium-doped bismuth selenide topological insulators. Topological insulators, or TIs, are bulk insulators in 2 to 3 dimensions and have gapless surface states where the charge carriers are Dirac fermions. These materials have strong spin-orbit coupling, and the surface states are protected by global time reversal symmetry. In the absence of a magnetic field or long-range magnetization, these materials possess a linear energy-momentum dispersion relation. However, in the presence of a magnetic field, global time reversal symmetry is broken and a gap proportional to the magnetization opens. In order to break time reversal symmetry, we can either apply an external perpendicular magnetic field, or we can introduce ferromagnetism with two possible strategies. 1. We can directly dope the Ti to create a ferromagnetic Ti, but we risk changing the band structure. Or strategy 2, bilayer samples. We can deposit a thin layer of pure Ti on top of the doped ferromagnetic Ti and therefore induce ferromagnetism and a gap via the proximity effect. Our bilayer samples were grown with molecular beam epitaxy. First, we use a substrate of indium phosphate, on which we then deposit 6 quintuple layers of chromium-doped bismuth selenide, our ferromagnetic Ti, on top of which we deposit 1 to 7 quintuple layers, or D1 layers, of pure bismuth-2 selenium-3, our pure Ti. We then study our samples with scanning tunneling microscopy, where we record both the topography and the spectroscopy of the sample. With STM being a surface measurement technique, the largest gap due to the surface state is the measured gap. We recorded the evolution of the spectroscopy and gap as a function of temperature and top layer thickness D1. The evolution of the spectrum differs according to D1 thickness. If the top layer is more than 4 quintuple layers thick, we can see that the spectrum remains gapless and Dirac-like for all temperatures, as we expect for pure bismuth selenide. However, for D1 less than or equal to 3, the gap opens at low temperatures, which is called the 2D Curie temperature, which occurs at 210 to 240 Kelvin. This non-monotonic temperature dependence of the gap is due to competing magnetic coupling components in the bilayer system. Next, we measured the effects of an applied magnetic field on gap distribution. We added magnetic fields of 1.5 to 3.5 Tesla, and we observed the gap clusters expand, becoming more homogeneous with increasing magnetic fields, such that at high fields the gap distribution looks uniform and the average gap value increases. This is consistent with the gap being associated with ferromagnetism. In zero fields, the gapped regions have out-of-plane ferromagnetism, whereas for the gapless areas there is in-plane magnetism. By adding an external perpendicular magnetic field, all the spins are aligned together along with the field, thus opening up a gap everywhere. Zero magnetic field. For a minority of spectra located only in gapless regions, we also observe spectral resonances resulting from magnetic impurities. These long-lived resonances are highly localized in size and are believed to be isolated chromium atoms diffused from the underlying chromium-doped layer to the interface. We may consider these in-plane isolated magnetic impurities as stable two-level topological bits, which may present interesting applications in quantum information technology. Thank you for your interest in our work and the New Journal of Physics.